Okay, last video here for 16.4. As we take a look at this one, there's a couple of things that we do want to talk about here. We have looked at pH curves already, just realizing that they are sketches. And with that, we can find, again, areas in there in which an equivalence point is reached. So you should be able to sketch these things when you do come across them on quizzes and tests. And now we're going to add in there, and you've seen a couple of examples already, adding in a relative pH. The very first sketch of a pH curve that we looked at in 16.4, we were doing a strong acid and a strong base. And most students in any class I ask this to are able to tell me that the neutralization point between two strong things is ultimately going to be a pH of 7. The pH that we get is actually determined by the entities that you see. We have in this unit then gone beyond what we saw with strong acids and strong bases. We've now included the weak acids and weak bases. And so you should take a peek at 761 and 762 for some pH generalizations when we take a look at the salt that's produced and how it relates to it. But ultimately, it boils down to this. All right, strong acid and strong base. All right, both are strong. We should have hydronium fighting with hydroxide. At the equivalence point, remember that that is the perfect 1-to-1 stoic ratio that we would have. So a perfect balance of the same number of hydronium as hydroxide should produce a pH of 7. And as I said, asking this at the beginning of this section to any Chem 30 class, I overwhelmingly hear from the students that, yeah, it's a pH of 7. We understand neutralization. The rest of it is taking a look at the various entities that we have. And it does boil down to things as simple as this. If I have a strong acid, all right, I'm looking at maximum hydronium. If I'm looking at a weak base, all right, then I'm talking about something that is producing a limited amount of hydroxide. When we take a look at these titration points, having something that overwhelms, or is a stronger acid than the weaker base, it makes sense that my pH at the equivalence point should be somewhere below 7. Better acid, more acidic. Therefore, a simplification here is that we just end up with something that is below 7 or in the acidic range when equivalence happens. Conversely then, if you're dealing with a strong base like a sodium hydroxide or lithium hydroxide, and a weak acid such as vinegar, your hydroxide donor here is going to be a little bit more aggressive, and we should see that equivalence is reached at a pH above 7 or in the basic range. How strong or how much this is, you do not have to calculate. That's going beyond our course. However, you may see sketches that actually have measured scales with diploma and unit exam questions, and we should just see numbers that match this generalization accordingly. The biggest part, or the most important part we have of this last segment here is talking about buffers. All right, when we talk about a buffer, there's a couple of different definitions that we can look at. Theoretically, a buffer is any solution that has a weak acid and its conjugate base pair in relatively equal concentrations in the solution. In other words, they are both present. Okay, so this would be any acid conjugate base pair that you can find from your table. When we were looking back at the first part of this unit and we were looking at that first page of our information, there it is. We had been talking about some of the entities in solution. We would probably say that in this region here, you would have a conjugate acid-base pair present in the solution. So that helps us work with the empirical definition. Empirical is what we can measure. And this is a solution capable of absorbing amounts of strong acid or base, but with only small changes in pH. Remember, in this one here, what we were doing is we were adding sodium hydroxide to a hydrochloric acid solution. And we're adding a strong acid, but we're not seeing pH increase rapidly here. So this is a good example of a buffered region just because we're seeing that marginal increase with additions of your acid or your base. So theoretically, we see that as relatively equal concentrations of acid conjugate base pairs being in there when you think about the entities. Or empirically, parts on your pH curve graphs that don't show large changes in pH as you are adding whatever titrant you might have. And so we're asked to look for buffering regions as we go through here. The buffering region is the area on a pH curve in which both the weak acid and its conjugate base are present in the solution. We could also add into this, and we see small changes in pH. All right, if we take a look at the titration of carbonic acid with sodium hydroxide, all right, down here, this is your sample. We have H2CO3 aqueous in our sample. The moment we start adding sodium hydroxide, hydroxide is added to the solution, taking the proton from your carbonic acid and producing HCO3 1-. And so the buffered region is sitting in here around region 1 because you do have an acid conjugate base pair, notice how they only differ by 1 proton, in the solution at the same time. But your carbonic acid, being the sample, will eventually run out. One more drop of hydroxide and boom, we go through an equivalence point. And then we get into a situation in which we saw with our polyprotic entities in the last one, you've got your bicarbonate ion now hanging out in solution here as the only proton donor left. If I keep adding sodium hydroxide, the H from HCO3 1- will go over to my hydroxide, leaving me with CO3 2- as the conjugate base. And so there is a second buffering region here, in this case, below the second equivalence point, in which we have relatively equal concentrations near the middle of this range, until you're just about out of HCO3, one more drop of your sodium hydroxide into the solution, and boom, you go through another equivalence point, and then you get into this region here in which water is the only last thing that we might have to accept or donate protons, and so that is not a buffering region. Word to the wise, the end of your titration curves is never buffered. All right, the only reason that we get any slope here is because it's the rate at which you might be doing titration error by leaving the burette open. So we end up with a buffering zone here, and a buffering zone here because of our conjugate acid-base pairs being in solution, and we see also a small change in pH during those ranges. Okay. Another example here, and we'll just take a look at one, is this bicarbonate ion buffer that we might have within our bloodstream. For example, all right, something I would talk about in class and get a few giggles out of is the fact that your breakfast, every morning you have it, is literally trying to kill you. No, it's not the choice of having really, really greasy bacon and lots of eggs and high cholesterol foods or anything like that. It has to do with something as simple as just the acidity or basicity of what you eat for breakfast. Let's go even more simple. Let's just talk about what you drink. So I have this in my bloodstream. All right, I have HCO3 1-. All right, it makes up a lot of the blood plasma. And with that, I have something that is amphiprotic. I have an H that I can donate in certain situations. I have a 1- charge, which means I can accept hydrogens in other situations. So for breakfast, to wash down whatever toast and jam you may have had, you take a big glass of orange juice, delicious fresh squeezed orange juice, and we wash that down. Well, orange juice is highly acidic. So think about what happens. You swallow the orange juice, it gets into your stomach, moves through the intestine, taking in all of those nutrients. You've also taken in a large amount of H+ or hydronium ions. If those hydronium ions end up in your bloodstream unchecked, then the pH of your blood is going to lower. Now, this is problematic. we know that we have hemoglobin in our red blood cells. Hemoglobin, a protein, does not like highly acidic environments. If we put hemoglobin into a highly acidic environment, it will denature, not too much differently than what happens to the egg whites when you subject them to heat. The proteins become fixed in one shape, and unfortunately, in their acidic shape, they don't bind with oxygen very well. This means that no matter how many breaths you take, you don't have hemoglobin to dissolve the oxygen to feed all of your cells. So, without having any way to prevent your blood from becoming acidic, then what ends up happening is hemoglobin denatures, and now I can only hold about 4 seconds of oxygen in my entire bloodstream, rather than 4 minutes. This could be a problem. Luckily, we have HCO3 1-. This is in our bloodstream, and it can be an acid or a base. If I was to introduce this to a whole bunch of bicarbonate ion, whole bunch of hydronium ion, then those hydrogens could go to the basic nature of this one. HCO3 would act as a base, making carbonic acid and reducing the hydronium in my bloodstream and preventing the pH from dropping. So, with this, my pH in my blood stays relatively constant so long as I don't drown myself in orange juice, and I'm able to survive the acidic nature of what I've just digested. Of course, there are limits to how far you can go with this, but for most normal meals, we don't put ourselves in any sort of acidic distress because there's enough bicarbonate ion hanging out here to accept any hydrogen plus or any protons that go into the bloodstream, shift its position here, act as a base, and keep things relatively neutral. Same thing, you're thinking, oh my God, I don't want to have to worry about doing that to myself with breakfast, so I'm going to drink something safer. I'm going to drink milk. Okay, milk is basic. If I drink basic milk, I end up basifying my blood. The pH rises, hemoglobin denatures again, can't hold oxygen or CO2, and I end up with 4 seconds of life between breaths rather than 4 minutes. Same problem happens. Luckily, bicarbonate ion in our bloodstream does have, hydrogens that can be donated to the hydroxide that have ended up in my bloodstream. And if I do, they go over to neutralize the hydroxide and make water, leaving the carbonate ion in its wake, but keeping the pH of my blood relatively stable and allowing me to survive a glass of milk as well. All of this stuff is described for you in greater detail, even with some pretty pictures, on page 764. We can take a look at some other ones on 765. All right, those just make really good context for test and diploma questions, fun things to talk about, and surviving breakfast was not something you were thinking about this morning. So we move on to a couple more examples here. All right, very similar to what we were doing. If we want to take a look at what is actually happening here and identify buffered regions or buffering areas within our pH curves, again, we need to see what entities we have at play and what reaction is going on. So I got a head start with this one. We took a look at what the entities are between the sample of sodium acetate and the titrant of hydrochloric acid. I have those dissociated products from my sample. I have those ionized entities from my HCl, and I have the water. When we look at the potential acids and bases, we don't see sodium ever playing. Acetate ion is a base, hydronium is an acid, chloride's not on there in any significant way, and we get those two. And so I have the strongest acid here, strongest base here, and I have a proton transfer in this direction. So if we take a look at the overall equation, hydronium donates its proton to the acetate ion. This again is a titration, so single arrow, to produce some water and some acetic acid. Okay, so we have that. We can see within here some acid and conjugate base pairs. So if we take a look at what's going on as we now start to sketch this one out, try and leave that on the screen. Gave myself not nearly enough room, but let's see if we can fix that. There we go. All right, so now we have the pH scale. We have the volume of our titrant added. Remember that our titrant was HCl. So we're starting off with a basic solution. Now in this one, you do have a weak base being titrated with a strong acid. So I'm expecting an equivalence point below 7. When I'm sketching this, I'll start out here, and I'm starting off with my acetate ion solution. And as I keep adding hydronium, the pH is moving closer and closer to neutral and the acidic range. Eventually, I will get down to just the last few acetate ions, and eventually an equivalence point will be reached. At this point, if I was to keep adding hydronium from my titrant, all right, the pH would continue to lower based upon the rate in which I add it. So if we take a look at where the midpoint is of this steep rise or drop, you can see that because of the strong acid, weak base nature, I should see an equivalent somewhere below 7. How far below it goes doesn't really matter. From there, we can call this a buffered zone. I see small changes in pH here, and if I take a look at it, I would have, from my equation, because I haven't used up all of this yet, CH3COO, a base, and the conjugate acid, both in the solution at the same time. So down here, I have CH3COO aqueous, and I have CH3COOH, both in the solution. I have a weak conjugate acid base pair, or in the order in which we look at this one, a base conjugate acid pair. Okay, so this is called a buffered zone because you have a weak acid relatively equal to a conjugate base in solution and small pH changes. Excuse me. Okay, this one is not a buffered zone because we have no weak acid and conjugate base pair other than water and your hydronium. And so with water is the only acid or base capable of continuing on in that titration, your titration is over and any pH changes just happen because you're acidifying or basifying your aqueous water solution. Cheat code then, the end of your titration curves, never buffered. Before the equivalence points, probably buffered, and you should be able to identify a weak acid conjugate base pair, from those. One more example to go. We'll take a look at this one. This one's very similar. We're just dealing with two very similar things. There are other examples that we could certainly do that have 2 or 3 steps. All right, but really we're just trying to identify the buffered zone from the unbuffered zone. For this one here, I have vinegar and I have water as my 2 acids. So vinegar is my strongest of the 2 acids. Hydroxide, very obviously the strongest base. This is my titrant and therefore an excess. This was my sample, and so I have limited supply. So if I write out my equation, acetic acid, otherwise known as vinegar, donates its proton to the hydroxides I am dropping into the solution. Single arrow, because of titration, I am forcing this to completion. And so in its wake, I can see that my vinegar solution gave up its hydrogen, or its proton, to hydroxide to make some liquid water. If we take a look at our pH curve now, as we observe this one here, you were starting out with a vinegar sample, which means I should be somewhere down here in the below 7 pH range. And as I add sodium hydroxide, my pH should be going up and up and up until I run out of it, and then I get a quantitative step, and then that just keeps increasing. All right, so my S-curves that I'm drawing on all these things are just relative sketches. You may be provided with more specific and accurate ones. You should never be asked to draw a very specific and accurate one. And so we look for the midpoint here, we take it back, And we can see that at the equivalence point, okay, we do see that our pH now here is greater than 7, simply because we did have a weak acid, strong base combination, and so we look for that particular position. Your buffered zone then is down here, because we see small changes in pH and we had vinegar in the solution along with the production of this. Go through the equivalence point. The end of your titration curve is not buffered simply because you're not going to have a weak acid conjugate base pair there, simply because water is the only player and you're just adding hydroxide to water directly. So you're just talking about changing the concentration of your solution. You're not talking about anything in that solution that can fight these pH changes. Okay, so there's your 2 examples, folks. That brings us to the end of the unit. And so you've got lots and lots of places to do some work. Please work with this buffered idea here on page 762, 766, and 767. And then time to move on to some of those reviews. Don't forget your textbook has a lot. Quest A Plus has diploma-style questions. Exam Bank has lots of little quizzes that you guys can do. And Solaro, as we've seen, does have lessons, practice questions, and practice tests. The nice thing about Solaro, we said, was that it's going to tell you where you need to go back and review if you're having any problems. That's it for equilibrium, folks. I hope you enjoyed it. Good luck with everything. And as always, any questions, just make sure you're asking.